Okay, today's lesson is going to be on multiplying and dividing numbers in scientific notation. In order to learn how to do this, let's take a look at standard numbers. So 2,000 times 40,000, you probably can do that in your head. Just doing 2 times 4 is 8, and then you know that you just add up all those zeros. There are 3 here, and there are 4 here. So 7 zeros. So the answer would be 80 million. Now let's look at how you can get that answer by putting these two numbers in scientific notation. If I wrote the number 2,000 in scientific notation, it would look like this. And if I wrote the number 40,000 in scientific notation, it would look like this. So now, how could I take these two numbers in scientific notation, multiply them, and get the same answer as 80 million? Well, you notice here how this is all multiplication. 2 times 10 to the third times 4 times 10 to the fourth. We know that multiplication is commutative, so we could rearrange these numbers. I could say that I could take 2 times 4, these two numbers first, times 10 to the third times 10 to the fourth. I could rewrite the problem like this. Then I know that 2 times 4 is 8. And here, if I want to take 10 to the third times 10 to the fourth, to multiply powers with the same base, I just add the exponents. So that would be times 10 to the 7th. Now, if I take this number and change it back to scientific notation, the decimal points right here, I'd want to move it 7 places to the right. 1, 2, 3, 4, 5, 6, 7. And if I fill all of these in with zeros, there would be 7 zeros, which would get me back to the 80 million that I started with right up here. So all we did was we multiplied the two coefficients, 2 times 4, and got 8, and then we multiplied the powers by adding the exponents. That's exactly how you do it. Okay, let's take a look at this one. Here we have 90 million divided by 2,000. So in order to do this without a calculator or even with a calculator, I can just take the 9 divided by 2, which is 4.5. And then, the 90 divided by 2, which is 45. I think that would work better. And then if I look at the remaining zeros, this is 6 zeros, and here there's 3 zeros. So if I take 6 zeros minus the 3 zeros, that would give me 3 zeros. So whether you do it with a calculator or without, I mean, you could just type this in a calculator and still get 45,000. Let's look at how would we get 45,000 if we were to do this with scientific notation. So let's change the 90 million into scientific notation. 3, 6, 7. And now I'm going to write the divide sign. And then 2,000. That would be scientific notation. Now, how am I going to end up getting 45,000? What would I have to do? Let's try and repeat this same process here. So I'm going to take a look first at the coefficients. And now remember, this is division. So if I take 9 divided by 2, that's 4.5. Now let's take a look at the exponents. 10 to the 7th power divided by 10 to the 3rd power. When we divide powers with the same base, we subtract the exponents. So 7 minus 3 would be 4. So now let's take this number, 4.5 times 10 to the 4th power, and let's just rewrite it and see if we get 45,000. Remember, it's going to move 4 places to the right. 1, 2, 3, 4, 0, 0, 0. And so you see here how after I move the decimal point, I would get 45,000, which is exactly the same answer we would get up here with a calculator or if we just did it in our head. So same process. I take the coefficients, I divide them, and then I take the powers and I divide them by using the rule, which in this case is subtracting the exponents. All right, let's take a look at a few examples where we're multiplying or dividing. We're going to start off here with multiplying. So I have two numbers in scientific notation that I want to multiply together. Notice they're very small numbers. They both have a negative exponent. Well, I know that in order to multiply this together, I can just multiply, right? Remember, this is multiply. I can multiply the two coefficients. Now this part you could use a calculator for, just the 2.6 times 1.8. And I get, with my calculator, 4.68. Now, to multiply the powers, because they have the same base here, I can just add the exponents. -5 plus -9, -14. Now I just want to check to be sure that this is correctly written in scientific notation. Remember, this first number should be between 1 and 9.9, and it is. So it looks like the best answer choice here is D. All right, example number 2. Here again, we want to look and we see that we're multiplying. So since everything's being multiplied together, to multiply two numbers in scientific notation, I first can multiply the coefficients with my calculator or without along here on the side. I'll just use the calculator, and when I use the calculator, I get 36.8. Now, let's multiply the powers. 10 to the 5th times 10 to the -3rd. To multiply powers with the same base, I add the exponents. So 5 plus a -3. That's 2. Now, take a look at your answer. This is not correctly written in scientific notation because this number is not in between 1 and 9.9. So I'm going to have to move that decimal point. When I move that decimal point, it's going to change this exponent. In order to decide how that exponent changes, let's take 36.8 and multiply it by 10 to the 2nd power. When I do that, it's going to take this decimal point and move it 2 places to the right. 1, 2, 3, 6, 8, 0. Now, here's my number. Let's take this number and correctly write it in scientific notation. The decimal point's right here. It needs to move 1, 2, 3 places. So this would be 3.68 times 10 to the, I moved it 3 places, 3rd. So this would be my final answer correctly written in scientific notation. Okay, example number 3. Here again, we are multiplying. These two sets of parentheses are stuck together. So to multiply, I want to first multiply the coefficients. You can multiply them in a calculator, and that would give you 66.616. Now I want to multiply the powers. 10 to the -4th times 10 to the -3rd. To multiply powers with the same base, I add the exponents. So -4 plus -1, -5. Now take a look at your answer and decide if it's correct. It isn't, because this number is not in between 1 and 9.9. This decimal point is going to have to move, but that's going to change the exponent. Let's see how it's going to change. I first want to take this number and I want to change it to a standard form. So -5 tells me I'm going to move this decimal point 5 places to the left. 1, 2, 3, 4, 5. 3 zeros. So 0.000666616. Here's the number in standard form. Now let's correctly write it in scientific notation. The decimal point is going to have to move right here. 1, 2, 3, 4 places. Because it moved 4 places, and this is a very small number, -4 is my exponent. And there is my final solution. If I multiply these numbers in scientific notation, this is the answer I get in scientific notation. Let's try number 4. Do you notice here now number 4 says we're going to divide? So we see division right here. So I have these two numbers that I want to divide. Sometimes it's a little bit easier to see this if I write it vertically. So if I were to write this as 5.2 times 10 to the 8th divided by 8 times 10 to the 3rd. It might make it a little bit easier to see what's happening. So just like multiplication, I can take these two coefficients right here and I can divide them. This is division. So using my calculator, I will divide them. And when I divide them, my calculator says 0.65. Okay, now I'm going to divide the powers. I have 10 to the 8th divided by 10 to the 3rd. And to divide powers with the same base, I subtract the exponents. So 8 minus 3 is 5. So then here's my solution. Only I notice here that this is incorrect. It has to be between 1 and 9.9, and it's not. So I'm going to need to move the decimal point, and then that's going to change this exponent. So do you see here how it says I'm going to multiply it by 10 to the 5th, this 5? That's how many places the decimal point needs to move. To the right, to make it a bigger number. 1, 2, 3, 4, 5, 0, 0, 0. So 65,000. Now let's change it correctly into scientific notation. Decimal points here, 1, 2, 3, 4 places. So this would be 6.5 times 10 to the 4th. And there we have our final solution. We took these two numbers, divided them, and we get this right here. All right, number 5. Looks like we're going to do another division. This time I'm not going to stack them on top of each other vertically. We'll just leave them out as they are. But I'm going to take this first number and divide it by 9.5. So in my calculator, I type in 4.75 divided by 9.5, and I get 0.5. Now let's do the powers. So here I have 10 to the 9th divided by 10 to the negative 2nd. To divide powers with the same base, I subtract the exponent. So negative 9 subtract negative 2. Do you see how that's adding? And I get negative 7. So here's my solution. But now I'm going to check it. And I notice when I check it that this right here is not in between 1 and 9.9. So I'm going to need to change this to a standard number and then back again into correct scientific notation. So negative 7 tells me 7 places the decimal moves to the left. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. There's my number. Now let's write it correctly in scientific notation. So the decimal point is going to have to move all the way over here to after the 5. 1, 2, 3, 4, 5, 6, 7, 8. So 5 times 10, 8 is my exponent. Remember, it was a very small number, so negative. So there we have it. There's our final solution. Answers written in scientific notation. All right, for our next few examples, we're going to see word problems where we're going to have to decide whether we want to multiply or divide in order to solve them. So let's look at our first one, example number 6. California, the most populous state, has approximately 4 times 10 to the 7th people living in it. The population of the entire United States is about 3 times 10 to the 8th people. About how many times greater is the population of the U.S. than the population of California? About how many times greater? Well, what are we going to have to do with these two numbers to figure out how many times greater? Am I going to have to multiply or am I going to have to divide? When it says how many times greater, here I got California. 4 times 10 to the 7th. And it says how many times greater is the population of the U.S. So how many times greater is going to be the population of the U.S.? 3 times 10 to the 8th. How many times bigger? Is it going to be 5 times bigger, 10 times bigger, 20 times bigger? Do you see, in order to get this number, I'd have to take the entire U.S. population and divide it by California's population to see what this number is going to be. So let's do that. Let's take the bigger number, the entire population of the U.S., and divide it by the population of just California. So here, in order to divide, I have to first divide the coefficients. 3 divided by 4 is 0.75. Then, to divide the powers, I subtract the exponents, and that would just be 10 to the 1st. So let's take a look here. I have 0.75 times 10 to the 1st. If I write this as a standard number, I would move the decimal point one place to the right, and this would be 7.5. So it looks like the population of the United States is 7.5 times as big, 7.5. So how many times greater is the population of the U.S.? About 7.5 times greater. Now, if I wanted to write my number in scientific notation, it would just be 7.5 times 10 to the 0, because that's already in scientific notation. Okay, number 7. It says here the circumference of the planet Jupiter is 2.7 times 10 to the 5th miles. So here we got Jupiter, and circumference means the distance all the way around the outside of the planet. The circumference of the moon is only 6.7 times 10 to the 3rd miles. So that's the distance all the way around the outside of the moon. Approximately how many trips around the moon would be the same distance as one trip around the planet Jupiter? So it's asking, how many times would I have to circle around the moon in order for it to be the same distance as just one time around Jupiter? Well, that's asking you, how many times bigger is Jupiter than the moon? So are you seeing this as a division problem? I am too. Let's take our bigger planet, which is Jupiter. We're going to take Jupiter, 2.7 times 10 to the 5th, and we're going to divide it by the circumference of the moon, 6.7 times 10 to the 3rd. Now let's see what we get. I want to first take the coefficients and divide them with my calculator. 2.7 divided by 6.7. Now I'm going to have to round this because the calculator gives me 0.40298. So I'm just going to go 0.403. Now let's divide the powers. To divide powers with the same base, I subtract the exponents. So 2. So now let's go ahead and change this into a standard number. 2 places to the right, once, twice. I get 40.3. Remember, that's approximately 40.3. So it looks like I would have to go around the moon about 40 times in order for it to be the same distance as one trip around the Jupiter. So how many trips? About 40.3 trips. Now this number is in a standard form. If I wanted to change it to scientific notation, the decimal point would have to move one place to the left. So that would be 4.03 times 10 to the 1st. Because in order to get it back to 40.3, I'd have to multiply it by 10 just one time, so it moves to the right. So here's standard form, here's scientific notation. Let's look at example number 8. The speed of light travels 3 times 10 to the 8th meters per second. So every second is traveling this far. How far can light travel in one day? There are this many seconds in a day, and it travels this far every single second. So the first second, it travels this far. The second second, it travels this far. The third second, it travels this far. Every single second. So how far could it travel in this many seconds? Are you seeing this as multiplication? Me too. So we're going to have to take how fast the speed of light travels in 1 second, and we're going to have to multiply it by how many seconds there are in one day. All right, let's see how far light's going to travel in one day. So we're going to have to first multiply our coefficients. And with a calculator, I'm getting 25.92. Now let's multiply our powers. Remember, to multiply powers with the same base, I add the exponents, so 12. Now I know that this number is not written correctly in scientific notation. Even though I see the answer choice right here, I'm not going to pick it. I know that the decimal point has to move. It's going to have to move between the 2 and the 5, which is going to change this exponent. But is it going to make the exponent go one lower or one higher? It's either going to bump up to a 13 or it's going to bump down to an 11. So which one's it going to be? I know when I move the decimal point, it's going to change, so it can't be this one either. Well, let's change it to a standard form number. This decimal point's right here. I want to multiply it by 10 to the 12th, so I'm going to move it 12 places to the right. 1, 2, and then 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which means 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. Now let's go back to correct scientific notation. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I'd have 2.592 times 10 to the 13th. My answer would be right here, choice A. That's how far light's going to travel in one day. Pretty far. All right, example number 9. If Americans can eat 8.5 times 10 to the 10th meals at restaurants each year, find the average number of meals per person that Americans eat yearly if the population is 3 times 10 to the 8th. This is how many people there are in the U.S. And Americans are eating this many meals a year. What's the average per person? that you would eat in a year. Well, we got to think about average here. Do you remember when you find the average, you add up all of the data and then you divide it by how many people there are. So in order to find the average, I'd want to add up all of the meals that Americans eat. And then I want to divide it by the number of people. Meals per person. So how many meals per one person? Well, let's take all the meals, and that's this many right here, 8.5 times 10 to the 10th, and we're going to divide it by how many people? 3 times 10 to the 8th. So this is meals per people. All right, let's first divide 8.5 divided by 3. The calculator says 2.83 repeating. Now, let's go ahead and divide the powers. In order to divide the powers, I subtract. So I get 2 right here. So this would be 2.83 times 10 to the second meals per person. Let's change this, since this is correctly written scientific notation, let's just quickly change this into a standard number. This decimal point will move 2 places to the right. So about 283 meals per person. And now that's yearly. So think about there's 365 days in a year. On average, people eat about 283 meals every single year out at restaurants. All right, last example, number 10. We have a certain bacteria that moves very slowly, taking steps that have a distance of 4 times 10 to the negative 7th meters each. So these are very, very small steps. If the bacteria takes this many steps, how far is it going to travel? So each step is this far, and we're going to be taking a lot of steps. How far is this going to travel? So this far, this many times. That's multiplication. You've got it. So let's take the distance that the bacteria moves in each step, and we're going to multiply it by how many steps that the bacteria is going to take total. And we're going to figure out how far it's going to travel. And of course, this is in meters. So multiplying, we're going to have to first multiply the coefficients. 4 times 3.25 is 13. Now let's go ahead and multiply the powers. Now if I'm multiplying powers with the same base, I add the exponents. Negative 7 plus 9 gives me 2. Okay, well notice that this isn't even written correctly in scientific notation. So I'm going to do that. The decimal point's here. It's going to move twice. 1, 2. So 1,300. So right here I have my standard number. How far is it going to travel? It's going to travel 1,300 meters. Wow, it's quite a ways. Now let's change it to scientific notation. I'd want the decimal point in between the 1 and the 3, 1.3. But that means that the decimal point, if it's right here, it's going to have to move 1, 2, 3 places. So times 10 to the third meters. So now if I go backward, multiplying by 10 to the third, it would go once, twice, 3 times, which would be 1,300. So my answer, in standard form and in scientific notation, this is how far the bacteria would move if each step is this big and it takes this many steps. And there you have it, multiplying and dividing with scientific notation.